Okay, YouTube, in this video we're going to cover some basics of functions, including what they are, how we write and graph them, as well as function notation, how we list the rules. So let's go ahead and start with the definition of a function. We say that a function is a rule that maps a set of input, or this is very important here, domain values, or we usually refer to domain values as x values, onto a set of output or range values. We want to be using domain and range to describe inputs mapping onto outputs. But to be specific, a function is a mapping of input values onto output values, or domain onto range values, in which every input value maps onto one and only one output value. So basically, another nifty way of saying this is that functions are one-to-one. And so you can see that I have a couple of mappings down here. This is what we refer to these as, but you'll notice that I have two different mappings where we map some input to output values here, or x's to y's. You'll notice here I have x mapping onto this right here, and we refer to this as f of x, or a function of x, and it means the same thing as y. But essentially my question here is, could we tell which one of these is a function? And I would say that clearly letter B is a function, and the reason why I would say that B is a function is because I notice that every single input over here only maps onto one output, okay? So we say that it is one-to-one, and really that's the vocabulary we want to be using. Whereas on letter A here, we have an input, or a domain value, 3, that maps onto two values in the range, 3 and 5. So we would say that this is not a function. And you could think of something as not being a function if it is just unreasonable. If you were to think about, say, temperature over time, you would never have a time or an input that would map onto two different temperatures. That's just kind of an absurd thing. So let's go ahead and talk about this second function here, or relation that I have here, that is a function. We say for the examples above, we can list the input-output pairs as ordered pairs. So in terms of vocabulary, we refer to ordered pairs as these x comma y pairs, where we say we have an input comma and output, or we call these solution pairs as well. And you'll see these sometimes listed as x comma f of x, which really just says this is the input value and this is the y value at that given x value. But we can list these as ordered pairs in a way that would indicate that when we say plugged in 1, we get 2 for an output. I can see that up here, or 2 maps onto 4, so 2 comma 4, and 3 6 and 4 8 respectively. But these are all of the ordered pairs that are representing this function that we see right here. And I guess, if we were to do what we normally do, we would graph these. Now, really quickly, let's review. We have 4 quadrants in our coordinate plane, 1, 2, 3, and 4. And just kind of talking about which axis is which, we say that this is our x-axis, this is our y-axis. So as far as quadrant 1 is concerned, talking about the basics, both x and y are going to be positive up here, whereas in quadrant 2 we have negative x values, since we're to the left of 0 on the number line, but positive y values. Quadrant 3 is unique. It is negative and negative. I guess they're all unique. And then we have positive x's and negative y's in the fourth quadrant. But to graph this functional relationship here, we'd say to graph 1, 2, we'd go right 1 and up 2. We just put a dot, okay? 2, 4, likewise, we're going to go right 2 up 4, right 3 up 6, and right 4 up 8. And you notice here, I hope, that there is a pattern. As a matter of fact, I'm noticing that with all of these inputs up here, really what we've done is doubled them to get the outputs. So if I were to say, using this pattern visually or, algebraically, if we were to insert 5 into this function, if I were to put in 5, what do we believe it would map onto? And I certainly believe that it would map onto 10. And we can see that on our graph here. It would proceed up to 10. So a function is a one-to-one mapping of inputs onto outputs, or domain values onto range values. So moving on really quickly, I want to express functions as a rule. And basically a rule, when we define a function, we often use a rule to describe the pattern that we're seeing. So for example, in the last one here, we looked at the rule as being, well, to get the output, you have to take 2 times the input. So writing our rules, we often write them as y as a function of x. And you'll notice that I say y equals 2x, or in this case, we're going to read this as f of x equals 2x. And I want you to know that these are the same things. F of x is the same thing as y. We could also use g of x, h of x. It doesn't matter what variable we use, but we're saying that y depends upon what x is in the first place, or it is a function of x. So you would read this second notation here. This is called function notation, but we would say f of x equals 2 times x. And really what it's saying is that the output value, or the domain value, is equal to twice the input value. So since we're going to use function notation and get used to that, let's go ahead and take a look at this example down here. But basically, if we are going to graph a function, what we're going to do is find some input-output pairs, okay, or ordered pairs. So I say this can be accomplished by creating a table of values. So you notice I have this t-chart here, x and y, where I can really say x, and I could call this g of x, which is our function here, g of x. and that is equal to 3x minus 1. Essentially, in terms of plugging in x values, we could use any x values we want. Now, a good range of x values, I hate to confuse you with the word range here, a good spread of x values, could be any x values, but would be -2 to 2 to start with here. But essentially what we're going to do is now we're going to go over here and say, well, what would our output be if our input is -2, and the rule is take the input times 3 and subtract 1 from it. So expressing this in function notation, we would say that g of -2 really is saying I am the output when x is equal to -2. So to find this, the first thing we do is we take out the x value and we substitute in the input value that we're looking for here, which is in this case is -2. Simplifying this, we get -6 minus 1. So in other words, our function value when x equals -2, our function value is going to be -7. So I'm going to go ahead and fill in the rest of these. For instance, g of -1 would just be 3 times -1 minus 1, which is -3 minus 1, which is -4. So we get -4 here. We say plugging in 0, one of my favorite things to plug in. As a matter of fact, when you plug in 0, it's going to eliminate that term right there. We just get left with -1. And I notice a pattern here. As a matter of fact, in this case, we say that this is a linear function, or a line, if you were to graph it. But I notice that it keeps going up by 3, or at least the value that I'm multiplying by the input here. So I get 3 times 1 minus 1 is 3 minus 1 is 2. If I see this pattern, though, this pattern here, we say that it's going up by 3 every time. We could use that to predict what comes next. So we could say, well, g of 2, I'm fairly certain is going to be 3 more than 2, which is 5. So very quickly here, I do want to graph these. We'd say left 2 and down 1, 2, 3, 4, 5, 6, 7. Left 1, down 1, 2, 3, 4. And then we have 0, -1, 1, comma 2, and 2, comma 5. But essentially the question I want to ask here is, should we connect the dots? And the answer in this case is yes. Yes, connect the dots. Connect dots. And the reason why is because technically we could plug in every single x value and get an output back. So we need to represent them all, and we say that every single point on this line represents an ordered pair that is on this relationship right here. So the last thing we want to make sure to do is label this, and we don't always have to call it 3x minus 1, but we say this is g of x right here. And these are all the points that if you were to say plug -2, 7 back in for x and y respectively, remember we start with y equals 3x minus 1, if we were to substitute for x and y and substitute -2 for x and -7 for y, you would see that we end up with a true statement, or just a statement that's valid. So when you look at the graph, the last thing we want to write in this video is basically this. This is the graph of all solutions of g of x. So those are what functions are, and those are how we graph them. In the next video we'll talk about how we transform them.